Hey everyone, this is your last video for Unit 6. So we are going to start talking about accumulation functions. So make sure you've got your packet open, follow along with me. I think this starts on page 52, something like that. Page 52, I think. So we first need to talk about what an accumulation function actually is. So an accumulation function is a function that is defined as an integral. So a lot of what we've been working with this chapter has been dealing with evaluating integrals. So we started out with doing using geometry, then we started approximating using the RRAM and the LRAM and the midpoint, and then we went to actually being able to do antiderivatives. So now we're going to talk about what an accumulation function is and how it's a function defined as an integral. So for example, we could have something that looks like this: g of x equals the integral of a different function. So in this case, I'm going to go ahead and do f of t dt. And our integral is usually defined as with a lower bound of a number and an upper bound of x. So g is the integral of this different function f. That means that g is our accumulation function. So we're going to look at what this actually means and how we can evaluate things using, or evaluate these accumulation functions, excuse me. So the graph of a function f is shown and consists of two line segments. False, it consists of 4 line segments, but whatever. Let g be the function defined by g equals the integral from 2 to x of f of t dt. Well, you can see right here then that g is an accumulation function because it's the integral of f of t dt, and it's the integral from 2 to x. So we need to actually figure out what this means. If I want to find g of 0, then I'm actually just going to go ahead, I'm going to start by just plugging it in here. So that means that they want the integral from 2 to 0 of f of t dt. So we need to kind of take a step back and think about what that actually means. All that is then, if I want an integral and I've got this graph, it just means find the area underneath the curve. So all I'm going to do is find the area. I want the area from 2 to 0. So hopefully you guys can recognize that that integral is backwards. So I'm actually going to go ahead and start by writing negative integral from 0 to 2 of f of t dt. So let's see, 0 to 2 means from here to here. So I want this area that's trapped between the curve and the x-axis. So it's this triangle right here. So let's see, negative, we've got 1/2 the base, which is 2, times the height, which is 4. And so what that means is g of 0 is actually going to equal -4. So again, all we did was actually find the area between 0 and 2 that's trapped underneath this function. That's all that ended up happening here. Let's take a look at part B. I want g of 2. Well, g is this accumulation function, so that means I want the integral from 2 to 2 of f of t dt. Hopefully you guys remember that's one of our properties, right? I can't find the area going from 2 to 2 because it means that there's no actual base for my shape there, which means this is actually just going to end up being 0. Alright, let's see. G of 1 means that I want the integral from 2 to 1 of f of t dt. So again, I'm going to go ahead and find an area. Well, 2 to 1, again, it's backwards, so I like to always rewrite then so that it's going the right way. So I'm going to do the negative integral from 1 to 2 of f of t dt. And let's see what that actually looks like. So starting at 1, ending at 2, we want this area in here, so that's a trapezoid, which means we need to remember the area of a trapezoid. So just in case you don't remember, it's h over 2 times b1 plus b2. So let's go ahead and do that. Let's see. We had that negative outside already. So the height is the distance between the two bases. So in this case, it's 1. So we're going to have a negative 1/2 times base 1, which is this height right here, so that's 2, plus this height right here, which is 4. So we get negative 1/2 of 6, so we get an area of negative 3. So anytime we're given an accumulation function, g, and we're asked for g of some number, we're asked to evaluate g, all we're doing then is evaluating these integrals. Alright, so I'm going to leave number 6, or part D, and I want you guys to try it, and I'm going to check in with you tomorrow on it. We can do it kind of as a warm-up. So let's go ahead and move on. Now we've got these same graphs of f, right? And if we look, we're given this accumulation function, g. So it's the same accumulation function that we had before. It's the integral from 2 to x of f of t dt. But now we're asked to evaluate some different things. If you look at all 4 parts here, now we're not evaluating the function g. We're trying to find g prime of 1 and g prime of 3, g prime of 4, g prime of 2, which means we actually need the derivative here. So before we even look at any of these problems, I just want to look at finding the derivative of this. So that means if I want g prime of x, it means I'm going to need to take the derivative with respect to x of this integral from 2 to x of f of t dt. So hopefully this looks super familiar to you. This is that fundamental theorem of calculus that we were just practicing and just learning. So this right here is that fundamental theorem of calculus that we did. If we're doing the derivative of an integral, we know that we can take our bounds and plug them in and multiply by the derivatives. So let's see here. That means the derivative from 2 to x of f of t dt is going to end up just being f of x. We would technically multiply this by 1 because the derivative of x is 1, and then we would subtract f of 2 times 0. So I can actually show that part to you guys if you want, just to clarify. So this is upper bound, lower bound, derivative of the upper bound, derivative of the lower bound, which means we end up just getting that g prime of x is equal to f of x, and that's going to be really important. So we use the fundamental theorem of calculus to work it out and get to what our derivative is actually equal to. So what that means then is if I want g prime of 1, that really means I just want f of 1. And since I'm given the function f, all I have to do is figure out what's the function value at 1. So here's 1. My function value is 2. It's as simple as that. If I want g prime of 3, well, we already said g prime of x is just f of x. So g prime of 3 is going to end up being f of 3, which means what's the function value at 3? So here's 3, here's my function value, and it's 2. Alright, we're going to go ahead and skip C and D so we can move on and get to the last part of this. So now we've done how do we evaluate an accumulation function, just g of x. How do we evaluate the first derivative of the accumulation function? And now we're going to be looking at evaluating the second derivative of the accumulation function. So we said on the last page that, well, here, I'm going to take a step back, sorry. There's my g of x. We said that g prime of x was equal to f of x. And we did that using the fundamental theorem of calculus. Well, now, if I want g double prime of x, that means I'm going to need to take the derivative of f. So g double prime, or the second derivative of my accumulation function, is really the first derivative of the function that was inside the integral. So g double prime is equal to f prime of x. Well, if we look, we're given the graph of f on each of these, the same as we were before. So the thing we have to remember is if we're looking for f prime and we're given the graph, we're really looking at the slope of f of x. So that's what we're going to kind of be using as we're evaluating the second derivative here. So let's try some. Let's see. G double prime of 1. So again, g double prime of x means f prime of x. So that means I'm going to need f prime of 1, which really means I need the slope of f at x equals 1. So here's x equals 1. I want to know what is the slope of the function at this point. Since this is a line, the slope of the function is just whatever the slope of this line is. So I'm going up 2 and over 1. That means this slope is 2. Alright, let's see. G double prime of 3 means I really want the first derivative of f at x equals 3. So here's x equals 3. I want the slope of this line. So I'm going down 2 and over 1. That's going to be negative 2. G double prime of 4.5 means we want f prime of 4.5. So we want the slope of f at x equals 4.5, which is roughly right here. But the slope of this line segment right here is clearly down 1 over 1, so it's negative 1. Alright, I'm going to leave part D so that we can talk about it in class. So I left a couple on each page for us to be able to kind of pull it together and talk about. But really the big idea here was that these accumulation functions are really just a function that's defined as an integral of another function. And so being able to evaluate it, we have to be able to look at areas under the curve, so the integrals. We have to be able to look at the first derivative and the second derivative of these accumulation functions. If you've got questions, please make sure you've got them written down, and we will talk in class. Thanks for watching.